8.3, we're going to look at how to estimate a population mean, make a confidence interval for a mean. You're going to see stuff that's very similar to what we did in 8.2 with proportions. So this would be the formula for a z interval, like we did for the proportions. But there's a problem with using this for means. This formula requires the population standard deviation. And if we don't know the population mean, we probably don't know the actual population standard deviation either. All right, so what some really smart people tried was, okay, let's just use SX, or the sample standard deviation, as an estimate. But when we do that, the confidence levels don't really work out. You can see they did a 99% confidence level, but only 92.5% of the intervals actually captured the mean. So that's no good either. So what we came up with is using what's called a T distribution. Okay, it looks similar to a normal distribution. It has that bell curve shape, but T distributions have more area under the tails, like the edges of the distribution, to kind of make up for the fact that we don't know the perfect standard deviation. All right, and so something to know about T distributions is there's a different T distribution for every sample size. We refer to it as degrees of freedom, and degrees of freedom is always going to be n minus 1, so sample size minus 1. So this is the formula that we are actually going to use. All right, and we're going to use our calculator to find that T star critical value. All right, it's going to be very similar to the way we did the Z star critical values in 8.2. Okay, so in your calculator, if you have a TI, you're going to go second distribution. For 8.2, we did inverse norm. For the mean, we're going to do inverse T because we're going to use that T distribution, okay? Area is going to be the same as it was for 8.2. So if I want a 95% confidence interval, the area that I want, I have 5% left over, and I divide that in half. So I want 2.5%. And then for degrees of freedom, that's going to be n minus 1. So this is a sample size of 12. So with that sample size of 12, that means I have 11 degrees of freedom. And I hit paste. And again, just like with the normal ones, it gives me a negative number, but I'm going to use the absolute value. So I would use 2.201 here. Casio, again, very similar to what we did in 8.2. So I'm going to go to menu and choose stat. I want distribution, so that's F5. This time we're doing T distributions, that's F2. And then my little computer version of the calculator does not have it, but yours will say above F3, it will say inverse T, and then you will enter in your area and degrees of freedom the same way that I just did it on the TI. All right, so just like we did for proportions, we also have conditions for doing a confidence interval for the mean. They're going to look familiar. So we have the random condition, it has to come from a random sample. We have the 10% condition. Again, our sample has to be less than 10% of the entire population. And then the last one we call the normal or large sample condition. Okay, for that condition, there are 3 different ways that it can be met. The first is if we know that our population has a normal distribution. So that would be just some information that's given to you in the problem. The second way would be if the sample size is large. And so by large, we mean the same thing we meant previously, that n is greater than or equal to 30. All right, if neither of those two are true, we can still potentially meet this condition if our sample data is roughly or approximately normal. Okay, so what we would do to test that is we would look at a graph. All right, and as long as it is not strongly skewed or contains outliers, then we are good. Okay, so we'll look at some examples of testing that normal large sample condition. So here we have a histogram that shows the GPA. Now, the shape of this histogram is irrelevant because our sample size is 50. All right, so sample size is bigger than 30, we're good. Normal large sample condition is met. Here, we have a sample size of 20, so that's smaller than 30, so now I have to look at the graph. They did a stem and leaf plot. There's, again, we saw the histogram in the last one. We'll look at dot plots, we'll look at box plots. Any graph can work. All right, so they did a stem and leaf here, and if I were sort of to sketch this distribution, all right, it would look like that. Okay, that distribution is definitely strongly skewed. Okay, there's more on the left side than the right, and these even could be outliers. So we would say no, the normal large sample condition is not met with this sample. All right, now we have another example here. Again, 20 students, so we need to look at some sort of graph. This time it's a box plot. Yes, this side is a little bit longer than that side, but it's not significant enough, and especially when we look at our box is pretty symmetric. So this is not significant enough to say that the condition is not met, okay? So it has to be something that is like super obvious. Big thing with box plots, remember, is anything in an AP setting that has a box plot, if there's an outlier, the outlier will be marked with like an asterisk or a little circle outside of the box plot. So if it does not have little dots out to the right or to the left, then there are no outliers. And that's usually a good indication that that condition has been met. All right, so once we have the conditions, then we can get to the work of constructing the interval. Same thing as we did before with our SPDC process, okay? So here's the example that we're going to work through. You can pause here and read this. I'm not going to read it to you. So we're going to construct a 95% confidence interval. So first in our state, we need to say what we are finding, a 95% confidence interval, and we need to define our parameter. So mu is the true mean number of books read by all American adults in the previous 12 months. Then for plan, we're going to check our conditions. They said it was a random sample, so that one's good. We could say 1520 is less than 10% of all American adults. That's a reasonable statement. And then our sample size is 1520, which is bigger than 30. So all of our conditions are met. For the do part, now we can use our formula. So we need to use technology or your calculator to find that T-star critical value. All right, and remember, your degrees of freedom is always one less than your sample size. And then we are plugging into that formula. So sample mean plus or minus T-star times the sample standard deviation divided by the square root of the sample size. All right, we do that math, simplify down to our interval of 11.09 to 12.91. Okay. And our conclusion, same formula for that conclusion sentence. We are blank % confident that the interval from, fill in the numbers, and then captures and write out your parameter in context of the problem. Okay, so same scenario there as what we did in 8.2. Okay, Pew has a report that American adults read an average of 14 books. Does our interval provide evidence that the mean is different in 2016? Yes, because 14 is not in our interval. Okay, so 14, according to this, is not a plausible value, so the average number of books people read must have changed. Okay, kind of just a little hint for you. If they're asking you in a free response situation to make a confidence interval, it's a safe bet that the conditions should be met. However, you still have to write out what those conditions are and show that they are met. Okay, so we can't just make that assumption in our work. You can make that assumption in your mind, knowing, okay, these conditions should be met, so let me make sure I write it out, but you have to write it out. Okay, so now we're going to look at an example where we just have some data. Okay, so again, you can pause and read that. All right, so same kind of process. We're going to state the interval and parameter. And then for our plan part, we're going to check conditions. We have a random sample. 20 is less than 10% of the terminals produced that day. And then for normal large sample, our sample size is 20. All right, so that means that we need to sketch a graph. So here you see a dot plot of this data from the problem. Okay, so they took this data, turned it into a dot plot. All right, this dot plot doesn't show me any skews. It doesn't show me any outliers. It's just pretty basic. All right, so I can look at this dot plot and say no strong skewness or outliers. That condition is met. Okay, this is important. I'm going to show you how to make some graphs on your calculator, but when you have to draw a sketch of that graph. It is not enough to just have it on your calculator. You have to draw it on your paper. It doesn't have to be really fancy, super straight lines drawn with a ruler, that kind of stuff. But there should be a rough sketch to show. And you don't, as far as the type of graph, you saw in this examples, we showed really all the graphs, a stem and leaf, a box plot, a histogram, a dot plot. My preference, the thing that I would suggest to you is a box plot. I'm going to show you how to do that on the calculator in another video. It's going to be the simplest to sketch out while also guaranteeing to show you the normality of your sample. So once we know those conditions are met, we can head to our formula, use our calculator to find the critical value and plug everything into a formula. All right, and then same interpretation template as before. All right, and then the last thing is just like we did with 8.2, sometimes we need to be able to come up with a good sample size to fit within a margin of error that we want. Okay. This is the formula that we're using for confidence intervals. However, if we're trying to come up with a sample size, we don't have data to have a sample standard deviation yet, and we also are trying to come up with a sample size, which makes it impossible to come up with our critical value because we don't know the sample size to know the degrees of freedom. So when we are doing sample size calculations, we're going to go back to that original formula that I told you not to use for confidence intervals. We're going to do some sort of pilot study to get an estimate for our standard deviation. And then we're going to use a Z critical value because we don't know the sample size, so we don't know the degrees of freedom. All right. Then just like we did in 8.2, once you get those numbers, you're going to plug them in and solve for N. Okay, so here we have an example. They want within 1 milligram this estimate of cholesterol in monkeys. Okay, so 1.96, that's the Z critical value that comes from a 95% confidence interval. It's from your calculator. 5 is the estimate for standard deviation, and then 1 is our margin of error. We solve this for N and get 96.04, which means that our sample size needs to be about 97 monkeys. Okay, something that you want to make sure that you get straight in your brain. Okay, when we are trying to find a sample size, we can use an estimate for population standard deviation, and we can use a Z critical value when we are trying to estimate sample size. When we are trying to do a confidence interval, the opposite is true. We're going to use sample standard deviation, SX, and we're going to use a T critical value because we know our sample size, so we know the degrees of freedom. All right, so make sure you get that straight in your brain and aren't finding the wrong critical value on your calculator when doing this math. Okay, that's all we got for 8.3.